Goedemiddag, dames en heren. En ek sien vanmiddag het professor Koopman gaan sit, want laas keer het ek vergeet om te sê hulle moet gaan sit. So baie dankie professor Koopman. So, ladies and gentlemen, welcome to the Faculty of Engineering and to the inaugural address of Professor van der Spuy. So, my name is Wikus van Niekerk. I'm currently the Dean of Engineering, and it's an honor to welcome everybody who's here physically present, but then also those who are online. We are really honored that you are here and you are virtually connected to us and part of the proceedings this afternoon. I specifically want to welcome our Deputy Vice-Chancellor, Social Impact Transformation and Personnel, Professor Nico Koopman. It's really an honor to have you here with us again, and we really appreciate that you made time to come and spend this time with us this afternoon. Also, our previous chair of the Department of Mechanical and Mechatronic Engineering, Professor Christian Skrewe. So actually now, this afternoon, he's doing Johan's job, because Johan is currently the chair, and now Christian has to stand in for Johan because he can't do two things at the same time. Of course, our honorary speaker, Professor van der Spuy, welcome that you are here. And then we have Professor van der Spuy's family here, Ilana, the wife, and the children, Adriana, Christel and Johan. Welkom, ons is baie bly dat julle hier so is en julle gaan saam met ons hierdie wonderlike geleentheid deurmaak. We also have to acknowledge Johan en Annemarie van der Spuy, die ouers van Professor van der Spuy. Hulle is aanlyn. Baie welkom en baie dankie dat u aanlyn is. Dan ook Peer en Erika Reuvers, die skoonouers van Professor van der Spuy, wat ook aanlyn is. Welkom vanmiddag. En dan Marie, of soos party mense haar ken, Maraai, van Bakstroom, die vrou van Professor van Bakstroom. Welkom hier by ons. En dan ook Professor Harms, Thomas Harms. Welcome again that you are here with us, Thomas. En dan, soos ons al ken, Tannie Termo, of meer bekend as mevrou Mimi Westdijk. Welkom hierso Mimi, ons is baie bly dat jy hierso by ons is. En soos jy sê, net seker maak dat hy maak nie 'n fout vanmiddag hierso op die skerm nie, dat jy net dit kan regmaak. Then, of course, we also have to welcome many other colleagues of the Department of Mechanical and Mechatronic Engineering, as well as other colleagues in the Faculty of Engineering. I see both Vice Deans are here as well. Then there are many friends, collaborators, students, and all the other people who are attending online. You are also welcome this afternoon. So it's really a pleasure for me to introduce Professor van der Spuy to you. And we made a selection of what we can say. Otherwise, there won't be time for him to make the most important contribution this afternoon. So he has held the position of professor at the University of Stellenbosch in the Department of Mechanical Engineering since 1 July 2020. Okay, so as you hear, he's a little bit late in making this inaugural lecture, but he's here now. He joined the department as a senior lecturer in 2006 with a specific emphasis on the lecturing of fluid mechanics and turbo machinery. His research focused on the development of turbo machinery for the South African industry. As such, the development of axial-flow fans and centrifugal compressors have become his passion. He is also a practicing engineer and spent 8 years in industry before returning to academia. He has worked within the mining industry, the petrochemical and automotive fields, and has been registered as a professional engineer since 2001. He has supervised more than 50 masters and 10 PhD students and published more than 40 peer-reviewed journal and conference papers. Johan is married, as we already heard, to the beautiful Ilana, his son Johan, which I believe is also studying or finishing engineering soon, and 2 daughters, Adriana and Christel. So Johan, the floor is all yours.
It's a privilege to be here, to see all of you. I have many thoughts about what should I say. So this afternoon I was standing in Marley's office and I was looking at the photo of Stellenbosch. You know that Stellenbosch is built at an angle. There are only two buildings in Stellenbosch that are not built at an angle. The one is Wilgenhof and the other one is the engineering faculty. Okay. Right, it's really a privilege to have my family here. I think it was Adriana, which she was about 6 years old. She said to me, okay, now my theme has been fans for so long, when is it going to change to something else? Because at school they always have to tell the teacher what their dad is doing. So, Adriana, I'm sorry, we're still busy with fans. And hopefully after today you'll have an idea of what I've been doing for the past, actually 30 years almost. I recall, so it's quite nice, Marie, for you to have you here. In 1993 I walked into Theo's office and I said to him, I want to design aeroplanes. And he said, oh, in South Africa there are not many companies designing aeroplanes. And he said, why? And I said, no, I like wings and wing profiles. And he said, well, do you know that a fan is actually a rotating wing? So you might as well design fans. And he caught me like that. And I've been on fans since 1994. So I've done my scriptsy, my thesis, and I spent some years in industry where I wasn't fanning for so much, but then afterwards I came back and it's been fans all along. And before I forget, I got a message this morning out of Italy to say there's been a change in time zones. They just want to make sure that they've got the time right. So I know there are quite a few of my friends from Italy also watching, and I hope you enjoy it. So starting off, so the talk today is about a very specific fan, and some of you would know the fan. It's referred to as the B fan, and I made a little sub heading saying how a local fan became an international star. Because I was quite surprised a few years ago. So this B fan was something that was designed here in the labs, and then a few years ago I got an email out of China, someone asking me for the details of this specific fan, because they're busy writing a paper and they're writing a paper about the B fan. So that's why it became an international star. So I always have to say what I'm going to say. So bit of background, why are we doing fans and what does the fan look like? Then we're going to talk about the B fan, and then we have to go technical a bit. I'm sorry, there will be some integrals and stuff, and look at the design, how we test it, and then how we simulated it. François, you're going to feature heavily here. And then some more simulation, and then eventually where we actually ended up installing it. And then where are we going with this? So when I talk about a fan, so I quickly ran into the office. Is this thing, it's okay, eh? Yeah. So I quickly ran into the office. I had to grab a fan blade. So this is something that a student printed a few years ago. The most important thing is that the fan, if you look at it, the blade has got an airfoil profile. So it looks like a wing. It's got a wing shape. Okay, so if you look at the fan itself, it's quite a simple object. It's not that difficult to imagine. So this entire component is called the rotor, because it rotates. It's got a shaft, and that little bit in the middle is called the hub, where we attach the blades to. And then we've got the rotor blades over there, and they sit in a casing, which we also call a shroud. And in this instance, the casing has got a bell mouth, so it's got a nice inlet to reduce the losses, so the flow likes coming into the fan. And then, importantly, between the blade and the casing, there's a bit of a clearance that we refer to as the tip clearance, and that also plays quite an important role in the design process. So this first bit of information, I knew about this paper for about 10 years now, that was written on fan energy consumption or electricity consumption actually in Europe. And when I knew I had to do the speech, I actually ordered the paper from Fraunhofer in Germany, and it actually arrived about 2 months ago. The astounding thing is that they reckoned in 2002 already that axial flow fans in Europe consume 200 billion kilowatt hours of electricity in a year. Now, to put that into perspective, I quickly jumped onto the wonderful internet Google. In South Africa, we consume more or less, depending on who you'd speak to, the same amount of electricity in a year. So, and the other thing that's important, we can save about, or the Europeans reckon they can save about 10 to 20% of this energy by just improving the design of the fan. Now, why is a fan so important for us? So fans give us the ability to remove heat from an object by means of convective heat transfer. So convective heat transfer is what you get when air or water flows over a surface, and then you get the transfer of heat or reduction or increase in temperature. And we can do that without using water. So we just blow air over an object. Why is it important to us that we can do it without using water? Because in South Africa, we don't really have a lot of water, but we've got a lot of heavy industries where we need the ability to cool. So this is a nice picture, very popular now with renewable energy being such a familiar topic. So this is a picture of the direct normal irradiation distribution in South Africa. And you can see we've got this beautiful red cloud there, more or less over the Northern Cape. The amount of solar, the DNI that we have in South Africa is only surpassed by Chile, the Atacama Desert. So we have immense resource in terms of solar. But look at the right-hand side map. So look at where the water distribution is. You can see where the solar is, there's no water. So if you need to dry, so if we want to utilize the energy there, you're going to need to do some form of cooling, and you don't have water. And believe me, you can't say it's the Orange River flowing through there. I don't know when last you drove over the Orange River in June. It reduces to a very small stream at certain times. So the use of the water from the Orange River is not really an option. So in South Africa, we actually, and very few people actually know that, we have the world's largest direct dry cool power stations. So this is a coal power station, so it's not solar. This is a photo I actually took when I visited. This is of the Matimba power station. And you can see there's a little man on a bicycle there. You can see the perspective and the size of this power station. And being dry cooled, it means that they use fans to condense the steam that comes off the turbine. So how a power station works, you take coal, burn the coal, you create steam. The steam is under pressure. You run the steam over a turbine that generates electricity. But to complete the cycle, so this is where the thermodynamics come in, you actually need to condense the steam back to water. And in South Africa, what we've managed to do at a very big scale is to use fans to do that condensation. So in this specific power station, there are 288 of these fans. Each of them has a diameter of about 10 meters, and it's 45 meters above ground level. So I don't know who of you have been 45 meters above ground. It's an interesting experience. So if you look at what is it all right? Okay. Hierin. Okay. Jy nou? So.
Ek dink daar is interference hier. So ons gaan maar die mikrofoon afsit vir die auditorium. Ons kan vir jou goed hoor.
Okay.
Ja.
Ja.
Okay,
Hierdie ene.
Sien nee, is hierdie een.
Hierdie ene.
Sit hom net af. As ek weer terugsit. Ja.
Perfect. Right. Great stuff. So nou gaan dit nie meer so aan en af klink, né? So sorry, I have to switch back to English. So So just looking at the picture, what does such an installation look like? So most importantly, the fan. The fan is what we're talking about. So you've got the fan over there, and then above the fan you have these fin tube bundles. They're arranged in an A-frame format, and this is where the steam gets condensed. So up here at the top is where the steam enters, gets condensed to water, and over there and gets pulled back into the power station. So you actually conserve the water. You don't evaporate the water into the atmosphere. So pretty much like almost like a car's radiator. You blow air over the radiator to actually remove heat. Other important thing is you look at this is the platform. We refer to this as the platform height. It's the height that you install this fan above ground level. It's a bit of relevance to it just now. So some pictures. So this is the Matimba installation. Standing below the installation, taking a photo up, you can actually see the fans there over there running. So this is a model of a fan. So this is just a model of an industrial fan that we built in our laboratories for purposes. It's actually it's a scale model of a typical industrial fan, but the size of that fan is small. The one that we built was actually for our purposes. We just built a small one. And we'll refer to it again later on in the discussion. One of the problems they have with these fans is when the wind blows over this power station, the fans that sit at the side of the power station. So you've got, normally the air would go through the fan like this. When the wind blows, that poor little fan sitting at the side, it's not a little fan, big fan, sitting there at the side actually experiences what they refer to as distorted inlet flow. So it struggles to get air through. And you get all kinds of problems with the ability of the plant. And if you actually visit these power plants, the people who run these power plants have become, that was initially one of the issues with these power plants, to get them to run stably. And the South Africans are really, really good at being able to run these power plants with wind blowing over them. But you do have occurrences where things can become a problem, and you can lose a bit of electricity, and then I don't want to say too much, but it can typically lead to load shedding. So back in 2005, Johan actually published a paper. And what he showed in the paper is that looking at different fans, you can actually find that they behave differently when they're exposed to this distorted inlet flow. And this is a measure which we define as the volumetric effectiveness, where we compare the volume flow going through the fan to the volume flow that would go through the fan under normal conditions, when it's just sitting out there on its own happily. And you can actually see that the different fans behave differently. And this is just given as platform height, but it actually represents distortion of the inlet flow. And over there, look out there, you see a name there already appearing. And part of this work actually showed that there's some potential in this fan that we refer to as the B fan. So enter the B fan. So this is our star. So the fan was designed by a person called Philip B. Bruno. So actually we have a bit of a thing going where we tend to name our fans after the people who designed them. So this was called the B fan. And it actually started as two fans. There were two. There's a B1 fan, which was designed. The only difference between the two fans, the B1 fan, the profile in the fan blade was a profile referred to as the Clark Y profile, and the B2 fan had a NASA LS profile. And the profiles, the one was supposed to do better than the other, and there's just a small difference in the performance of the fan. The fan was designed to a very specific specification, and this specification over here is actually a scaled power plant spec. So it's scaled from an existing power plant, and when I say scaled, it's scaled to the size of the test facility that we have here at the university. And you can see there, the important thing is the pressure, 200 pascals sounds like a lot, but actually if you measure it in water, it's 20 millimeters of water, so it's nothing. A volume flow rate, and there was a certain fan shaft power and a rotational speed that it had to adhere to. So this is where the equations come in. When you design a fan, you start with the velocity triangles. And I say to the students, when you do turbo machinery, there are a few things you need to know. And the first thing is velocity triangles. And what the velocity triangles, what the velocity triangles show is the behavior of this rotating blade. So you can in your mind actually see this blade moving through the air. And what happens is the air comes, if you stand to the side. Now this is what I teach my students. So if you get this, you're very good. You can go third year. So Johan, this is preparation for your exam in 2 weeks' time. So when you stand to the side in what we refer to as the absolute reference frame, you will see the air moving straight into the fan. Or it can be distorted, but let's say for straight. But this blade is actually rotating at a speed what we refer to as U, which we write as omega R, and omega is the radians per second, the RPM, the speed at which the fan runs, and R is the radius of the fan blade, so at different places it's got different radii. And you put that together with that, you actually get the relative flow, the relative angle at which the flow is going to see this blade as it moves. The flow will go over the blade, and hopefully it's well designed, so it will follow the blade nicely, and it's going to leave the blade at a relative vector omega W2. But you standing to the side, you're not sitting on the fan blade, so what are you going to see? So to be able to see the absolute vector, you need to add that rotational speed, which is omega R, to that relative vector, and then you get your absolute vector over there. And this is what you will see if you stand to the side. So importantly, we measure the energy transfer to the fan using this Euler equation, and written in terms of energy per second per unit mass. It's energy transferred per unit mass. It's written as omega R C theta 2R, which C theta is the, in Afrikaans, what Theo always used to say, the soos jy die lig klap. So as you hit the air, that is that C theta 2. And that is an indication of the energy that you transfer. So that's quite an important equation. When you design the fan, so what you want to do, you first want to figure out what the size of the hub of this inner part is going to be. Because once you have that, then you know what the length of the blade is going to be. If you've got the length of the blade, then you can design that velocity distribution out of the blade. If you've got the velocity distribution, you know what the energy transfer is going to be. If you know what the energy transfer is going to be and you've got the efficiency, you can work back to the pressure rise. Okay, so we need to know what the hub diameter is going to be. And there was a guy called, I can't remember his first name because, Fransje, you've got the book still. Van Niekerk. His surname is Van Niekerk. And he published, actually in 1950, I think his thesis was published in about 1956 or 58. He published a work on how he developed this equation to calculate the optimum hub diameter of a fan for certain lift to drag ratios, for certain amount of swirl at the hub. So the swirl at the hub is that C theta 2 that you would exert at the hub, and then flow coefficient at the tip. And all basically depending on the design parameters that you want. And he developed this equation, and from there you could then get an optimum hub to tip ratio for a certain efficiency that you want for the fan, and that gives you the size of the hub. Note that there's actually a limit to the amount of swirl you can put at the hub, because that helps you to solve it. Otherwise, you're going to be very busy and design fans that don't work as they should be. So there's a limit to the amount of swirl you can exert at the hub of the fan. And Wallace is also quite a popular author, used to be, on axial flow fans. He prescribed a limit of 1.1 to this swirl at the hub. An interesting thing, there's quite a well-known textbook by Dixon that they use in turbo machinery. And in that textbook, it's an international textbook, there are only 2 South African names that I could find in that textbook over the years. One of them is actually Van Niekerk, and the other one is Professor Graham Smith at UKZN. Actually get referenced in that textbook. So, okay, so now we've got the hub tip ratio, and then it actually is just mathematics. So we now need to design that outlet swirl angle so we can, our swirl distribution. So you can assume different equations for the swirl distribution. So we usually use that format AR to the power N. And then we have this thing that we call the simple radial equilibrium, and basically what it does, it balances this flow distribution, the swirl, and the axial flow through the fan with the pressure distribution over the fan blade. So it's just an equation that balances actually all the forces in the radial direction, and from there you can actually then see what the velocity distribution in the fan would look like. Then you get an equation for the total pressure downstream of the fan is then given by that, and this is where we integrate. So I always believe you'd spend 2 years learning integration, so you need to use it somewhere, so we need to integrate. And so the other question is, what is an integral? It's a very, very elegant summation. So what we actually do with the integral, we actually just sum that together over all the different radii. And if you're not a clever engineer, that's like me, you actually can do this integral in parts, and you just break the blade into different radii, and you actually just add the different energies together. So then we can calculate. So for our cooling fans, we like working with what we refer to as the fan static pressure. And the fan static pressure is actually referred to as the difference between the static pressure downstream of the fan and the total pressure upstream of the fan. And why that is, it's because in our installed condition, when this fan works in the power plant, the energy that's downstream of the fan is actually lost. And I know there's a lot of contentious issues around that, what actually happens to it, but for our purposes, the energy is gone. And that's why we work with fan static pressure, and it can, to the people who are not really familiar with fans, it can create a lot of confusion because that term actually means a total to static and not just static. Then we have the dynamic pressure downstream of the fan, and well, to get that static, we take the total pressure that we had on the previous page, and we take our dynamic pressure that we had, and we subtract that, and we get our static pressure downstream of the fan, and once again we integrate that to get it over the blade. And then we can have a theoretical fan static efficiency, which is basically just what we get compared to the ideal, the maximum we can get, which is that fan static pressure compared to the fan total pressure. At this stage, there are no losses in these equations. The losses come later. So from what Philip did, Philip then did these calculations, and he found that for a hub tip ratio of 0.4, more or less there, he gets the required pressure rise, and he gets a nice high efficiency in the 60%, which was relatively high. Well, we didn't think much of it, but we later realized it was actually quite good. And this graph actually comes was actually recreated by Francois. It actually comes from Philip's thesis. And then once he's done that, he actually ended up with a velocity profile, which was a combination of what we refer to as a free vortex profile towards the tip, and towards the end he had a quadratic profile over the inner half, and that limited the amount of swirl at the hub. So I just be careful what I say. We actually found, so what happened is, Francois, we wrote a paper about Philip's design in 2012, and we actually found there was a small mistake, but the fan was still performing, so it's fine. So now we've done that, we've got the velocity, and from the velocity we can get the angles over the blade, and then there's this wonderful equation that says that the lift coefficient over the blade times the solidity, and solidity is just an indication of the width of the blade, is given by these angles. And that enables us then to say, okay, we want this fan blade to have a certain size, usually dictated by what your manufacturing capabilities are, and we can couple that to what the lift coefficient at the hub and at the tip of the fan blade will be, and you'll later see, I'll show a picture. as with any normal aeroplane wing, there's a limit in terms of the amount of lift you can get for it. If your lift coefficient goes too high, you actually run into stall. So the fan wouldn't fall, the plane will fall, but the fan will not fall. The fan will just be very ineffective. So if you go too high on that lift coefficient, you're running into problems. So you have to balance the size of the fan to the lift capability of the wing. And then you end up with this profile, which is a blade stagger distribution, which is just very nice blade profiles all along the radius. So all this picture does, it just stacks the change in blade profiles at different radii, and this is actually the secret, because this tells you what the fan looks like. And I've spent many hours sitting there literally with a vernier and measuring in Philip's thesis the length of the profiles, because the thesis, that stage, things weren't as electronic as they are today. And then Philip ended up with a fan. So this is actually quite a unique photo. At some stage it was displayed here in the faculty. And the two B1 and B2 fans were manufactured using NC machining, which was quite advanced in those days. Manufactured the plugs, and then drawing composite molds of the plugs. And then the blades were made from two halves that were glued together. And this is a photo of the fan. I don't know if this is the B1 or B2 fan. Actually in the test facility with Philip sitting there with his scale ruler, we actually made some fun of him, because that was just a pose. I don't know why he had the ruler there. He couldn't do it. Doesn't mean anything. One thing that you can note from this photo is that if you look carefully, you'll see that there's a small little gap between the blade and the hub there. And that was something that what Philip at that stage didn't do. We call it wrapping. He didn't wrap the bottom of the blade. The flow, when the blade rotates, the flow doesn't go straight through the blade. It actually goes like this over the blade. So you need to create your profiles also at the radius. So Philip didn't do that, and we didn't think much of it at that stage. We actually realized later that had a bit of an influence. And this is a photo in 2012. So for different reasons, we destroyed the fan, and we actually remanufactured the B2 fan. And now by then we named it the B2A fan. So I can go into the history why we took the B2 fan and not the B1 fan, but there's actually a very simple reason, and I don't want to go into that because it's actually very simple. It was just easier to manufacture. So we took the B2 fan and we remanufactured it, and we actually wrapped it. It referred to as the B2A fan. So this manufacturing was actually done, a lot of it was done by Francois in his PhD. He actually also took this very nice photo. It doesn't look exactly like this anymore because we've scraped off a lot of the paint on the inside, but someday we should actually just repair it for the photo again. This fan actually we still use quite a lot. In our work, the specific B2A fan. And what has happened since then, people just started referring to the B fan. It just became the B fan. B2, B2A, B1, it just becomes too complicated, and now we just refer to it as the B fan. We tested it. Just look at the time, we're still good. So we actually tested it in this ISO 5801 type A fan test facility, and type A means that we tested to get fan static pressure, specifically related to that static pressure definition that I said earlier. Actually, I see Gerard here. So this facility was actually built by Gerard's elder brother Sarel as part of his PhD. Way back in 1990 already. We've actually since then, Kobus actually helped when Ferry, we put up a roof over here. It's still running, and it's still actually in quite a good condition. So what does the test facility look like? So important, our test fan actually sits here at the back of the facility, because we're trying to simulate this effect where the fan blows air out into the atmosphere and we lose all that energy. So upstream of the fan we have this settling chamber, and this is where we measure the pressure. So we measure the pressure at the side of this room relative to the atmosphere, and that tells us what the pressure rise of the fan is going to be. Oh, there's a few other things you need to add. And then to know how much air is going through the fan, we actually have another, so there's a bell mouth and there's another bell mouth. This bell mouth is the one that goes with the fan. The bell mouth at the front there actually is where we measure the flow rate. I wish I could have had my Scripsy student here, because the other day I had to explain to him how a Bernoulli flow meter works. This is what they call a Bernoulli flow meter. And actually it's a means of measuring the flow rate. And all these things, the settling chamber, and this ducting in front of the fan actually means that we lose some energy in the process of testing the fan. So to overcome that energy we lose, we've got the booster fan here. And the booster fan, all it does, it just puts back the energy that we lose due to the fact that we're testing the fan. So we can actually then test the fan to a point where there's no pressure difference over the fan by using that booster fan. You'll see it in the graphs. Okay, and what we measure the fan static pressure, way back to our calculation that we showed just now. We measure the fan static pressure, and it's basically just the difference between the total pressure upstream of the fan and the static pressure downstream of the fan, which is the ambient pressure. We measure fan shaft power, which is just the power that goes into the shaft that runs into the fan, and from there we calculate efficiency, which is just the pressure rise times flow rate divided by fan shaft power. So we actually saw that we really struggled to make. So what we then did is we tried to model the fan in what we call CFD, which is computational fluid dynamics, where we then, so what computational fluid dynamics does, it's a computer simulation of what happens over the fan, and you basically break the air or the volume around the fan into little elements, and you calculate the flow through each little element, and you add all of them together, and then you can actually see what happens in the bigger domain, and that's computational fluid dynamics, or short is CFD. And this model actually represents what we had on the previous page over here. So it represents this chamber upstream of the fan, and then this big outlet which goes into the atmosphere. And this was done using specific software, ANSYS Fluent. We did numerous investigations on this. We had different, we tried different software packages. We tried Numica, we tried Fluent, and we tried Fluent again. By the time we got it right, it was ANSYS. Actually, the first person who got the calculations right was Francois, and I distinctly remember showing this to my co-supervisor for my PhD, Professor Detlef Krieger. I showed him the first time we got these simulations right, and Detlef said, "Okay, you're done. I'm happy. We managed to do it." So the simulation represents this fan blade. So there you can see a nice model of the fan blade. There are 8 blades, but you don't need to model all 8 of them. You only need to model one, because all the rest does the same than that one. So you just model one and you add all of them together. You can see some specifications for the cells. We actually used hexahedrals, which gives a very nice mesh over the fan. It's a very efficient way of actually solving the flow of the fan blade. And what we did is, for our model on the previous page, we said we've got a certain mass flow going in here, and we monitored the pressure rise over the fan. And then we got these results. So on the left, you would see these are the original test curves that comes from Philip's work, and these are the test curves that was published in, I think this was in 2014's ASME paper, Francois, if I'm not mistaken. And you can actually see there numerous tests, a large number of tests, and you can actually see the CFD actually correlating quite well with the test results. This correlation between this curve shows volume flow rate and static pressure through the fan. This correlation it had been achieved previously, but the one thing that we were really excited about is for the first time we actually managed to get the efficiency right. So you can see the efficiency that Philip measured, and you can see the efficiency that we ended up measuring and simulating. And what you note, first of all, is that the efficiency is slightly higher than what Philip measured. And you can see the correlation that is so good. And that is actually where we did that wrapping of the fan blade onto the cylinder. That was why we eventually managed to get this simulation right. The fact that the fan blade profiles were straight compared to wrapping them made a 1 degree difference in the effective angle of the fan blade, and that's why we couldn't get these things to correlate. In any case, so we got that. Then, but that was not finished. So eventual aim, by then, we were quite set on, the intention was to get this fan into a power plant. So then we simulated the fan in an installed condition. So this is simulating the fan inside a air-cooled condenser installation. And you can see there's our A-frame, there's our fan at the bottom there. And but this, you remember we said they've got about 288 of these fans installed, so you can't do just one, you have to do many of them. And the way to do that, so you can't model each little fan blade element if you want to model 288 fans, so in this case we actually did 30 fans. You actually represent this fan blade by forces. So remember I said this is just an aircraft wing, and this wing has got a certain lift and a certain drag profile. So you can actually break that back into little wing profiles. You can work that back into force elements and then say in your simulation, I'm not going to model the fan blade, I'm just going to add the forces in my simulation based on what I know about wing profiles and the ability of the fan blade to actually generate lift. You can see that straight line actually means something there, and that is the effect of, in a rotation, when the blade is rotating, you actually get the effect of this lift being extended. It doesn't stall as easily. And we incorporated that into the model. This was work done by Johan Engelbrecht in his PhD. He built an ACC of 30 fans, and he modeled the effect of wind over the ACC. Think back right at the beginning, I said to you, we saw that different fans behave differently under wind. You can see there's the mesh of our CFD, the same principle that we had with our little flow elements, all that stuff. The wind going over the ACC, and he then looked at, see how much air is actually going to go through the fan. So we can see what the effect of this distortion is going to be on the fan. And we compared three different configurations. We had our, what we refer to as our A fan, which is the industry fan. I showed you the picture at the beginning. We had our B fan, which is our champion. And then we combined the two. We said, well, maybe you want to save a bit of cost. And what's going to happen if you only put the B fans at the side of your plant where you know the wind effect's going to be quite bad? So we had there are many comparisons, but the one that says the most is the one where you compare the power absorbed by the fan to the amount of heat transferred by the air. And you can clearly see that this, our B fan, gave the best results compared to the industry fan and the combination of the two. So this came from Johan's work. And then we were quite fortunate or privileged by the help with our industry partners. I know Albert and Hanu actually put quite an effort into us being able to get this project. We got a funded project from the European Union. We call it the Min-Water CSP project, and this enabled us to actually manufacture the fan. So now we've tested scaled fans. I mean, we've been testing, Philip did the first test in the 92, 93, and so now we were at about 2015, and we got the 2016, and we actually got the opportunity to build this fan in its full size of 10 meters. The fan was manufactured by a company, and I don't know where Chris is. I specifically said to him he had to be here. It was my other colleague, Chris Meyer. A company, Notice Fan Engineering, built the fan, constructed the fan. And these are just some photos in our structures laboratory. We actually tested the fan blade. By now, we were aiming to install this fan in a running power plant. And so I actually had to sign, as a professional engineer, I had to sign off on the fan. And we made quite sure that it was actually strong enough that it's not going to break. We found that we loaded it with sandbags on the blade. We clamped it down at the one end, and we loaded it with sandbags, and we saw that it failed at about 2.8 times the operating load of the fan, so we knew we would be relatively safe. And then we installed the fan. So this is quite a famous picture that we took of the fan installation. The person who took the picture was Francois. And if you actually see there, that arm sticking out there is actually Donnie Els, and that's Chris Meyer and me, and another Francois, Nel, is actually an ex-student of Eskom, and we actually installed the fan at Matimba. It's quite an experience. You stand on this grid, it's a 4 millimeters thick, and you've got 45 meters of air underneath you. So this work was actually supposed to be done by Eskom, but they couldn't. So we ended up doing it. And this was the fan installed, so I hope it's going to run. I checked this morning. So let me just tell the story before I run the video. So they switched the fan on, and then we were not there because for safety, we were actually standing 45 meters below, looking at the fan. They switched it on, and then they radioed us and said, well, there's a problem with the fan. It's not pulling amps. So we all walked up. We got there and we said, stop the fan, and Francois put his camera out there, and they switched it on again, and this was actually taken, and that's the fan running. So it's actually the second time they ran the fan. So that was the second time they ran the fan. What we afterwards realized when they phoned us and said that the fan is not pulling amps, the difference in amps was more or less the increase in efficiency of the fan. So actually, it was quite good. And this is a photo from the bottom. Actually, this was taken, I think, the next morning. We were quite tired after doing that. That photo was taken about 7:30, about 8 o'clock at night, the previous one, when we got it to run. And this was, you can actually see, there's the fan running in the power plant. And what is quite unique, this fan has been running, this was October 2016, so we are 5 years ago, just over more than 2 weeks, 5 years and 2 weeks ago, and it's been running ever since. Okay, but nothing is perfect, there are one or two issues, but it's still running, so it's still at the plant. And we actually were quite thorough, so we actually did some measurements to compare the fan its performance. We actually went and we installed anemometers on the plant to measure the flow rate through the fan to make sure that it actually performs as it's supposed to be. You can see there's a small difference in what we expected the volume flow rate to be and what the actual volume flow rate through the fan is, but the fan is doing what it's supposed to do. So, to conclude, we had we designed, or Philip actually designed, a large diameter axial flow fan. We tested the fan numerous times over many years, and we eventually manufactured the fan locally. So it's quite important to realize this fan was done, it was developed here, it was manufactured here, and it is tested here. So everything was done locally. And we ended up with a fan with a relatively large hub diameter, which was, we actually got some criticism for that large hub, and there was a bit of engineering involved to make it work, because you sit with quite a large disk that you actually had to install eventually. The efficiency was above 60%. We didn't think much of it until we actually started realizing that it's quite good. We were at conferences, I know at one conference, the efficiency, we were quoting efficiency values of 65, and people actually came to us and said, oh, we contest that. We don't think it's really that possible, and it is actually possible. We showed that the fan actually outperforms other fans in the ACC when we simulated it. The fan, on-site installation showed that the fan performed as expected, and most importantly, it showed that we can do it locally. And then finally, the purpose of the university is actually not conquering the fan industry. I think that should be made quite clear. We don't want to be in the fan manufacturing industry, but our focus is actually to create opportunities for our students, our researchers, and then for local industry with projects like this. Just some references, and then just acknowledgements specifically to the work. I want to thank the many persons and industries, companies that were involved and contributed towards this work over the last 30 years. Most of all, not least of all, the postgraduate students and the researchers. That it was not just me, there are many researchers that spent hours on this thing, and they tried to show the merit of actually what was a relatively simple piece of engineering work. Many of the persons actually, if you want the names, are mentioned in the references. A special mention should be made, once again, to the regional designer, Mr. Philip B. Bruno Bfan. And then I also want to end by saying a special word to Professor van Balkstrom and Krieger, who's, so they're very special to us. And their vision actually enabled us to do what we're doing today. So with that, thank you very much. Is dit nou hierdie in en nee?
Professor van Niekerk, Prof Celestie Viljoen, Prof Schrewe, colleagues, students, guests, especially family and friends and mentors of Prof van der Spuy. It is great to participate in this special moment, and it is always great to be in the company of engineers. They always give you that feeling that, yes, we can. Let's not battle with this, man. We can get a solution for it. Prof Petrie, I see you nodding at that. Professor van der Spuy, you have shared with us the story of a fan. When I saw fan, I was wondering, oh, this might be a combination of Marty sport and engineering. And then I saw, no, start reading, it's about a wire. You shared with us the story of a fan from its birth. A fan is born, you titled your professorial inaugural address. A fan for a hot and dry climate, a fan for the continuous cooling of processed fluids in heavy industries, a fan with a story, a story that creates new fans and new fan stories of both high stability and high efficiency, specifically of high fan static efficiency. Your fan story demonstrates to us the nature of knowledge that universities, to put it simplistically, that universities seek, that we transmit, and that we apply. Our knowledge is research and informed, and research informing. Our knowledge is about lifelong learning and teaching. Our knowledge is about reciprocal social impact. It is about society impacting on us and co-determining our research and teaching agendas, and about us impacting on the concerns and needs, the opportunities and the innovation quests of society and industry. The knowledge that you display tonight and that you profess as full professor of Stellenbosch University contributes to the building of a society where humans and nature can enjoy higher levels of dignified and quality living. So please accept our word of congratulations to you and your dear ones. Congratulations also to your department and to your broader faculty. Congratulations to your colleagues, your students whom you recognized, and your industry partners. Prof. Johan, on behalf of our Rector, Prof. Wim de Villiers, I gladly hand this certificate to you. To have you as a colleague at our institution is fantastic.
Good evening, colleagues. Thank you for attending. It's my privilege to just say thank you. So first of all, for the man of the hour, thank you, Johan, for a wonderful presentation and an overview of your work. It's characteristic of Johan that he gives credit to a lot of other peoples and do not acknowledge himself. So we know that you stand here because you've done remarkable work over the years, and well done on that, and we look forward to all your contributions into the future. I was racking my brain in the presentation to respond with a load shedding joke, but he's reassured me now, so I've got a lot of confidence in the future. So Johan, thanks for that. Then thank you for all the current colleagues and former colleagues that are here present and attending this meeting. I see very well-known faces here, Mimi and Theo and Thomas and Hanu, I saw somewhere. So thank you for all of you attending. I also thank all the current and former students here present, so thank you for your attendance here. Then Marley has given me a list of people that I must thank. So first of all, Marley, thank you for this list. We would like to thank the corporate communication, specifically Olivia Adams and Amira Brown for their arrangements and arranging the snacks afterwards. We would also like to thank the coordinator of publications and within the Center for Governance Function Support, that is Mr. Jonathan Blankenberg. And we would like to thank Justin Alberts for the recording and live streaming of this event, and I'm sure that people online really appreciate that. And then last but not least, Professor Koopman, thank you very much for your attendance. We know, well, I know from a past conversation that you almost studied engineering, so I trust that you enjoy the time here, and we really appreciate your presence here and your really spot-on response to the presentation. Thank you very much for that. Then, friends, colleagues, there's something to eat and drink outside, so you're welcome to come outside and enjoy the time with Johan and his family, and we look forward to see you there. Thank you very much.